October 29th, 2025. The day 3I Atlas reached its perihelion, the closest point to the Sun. Something occurred that defied every explanation. For weeks leading up to this moment, the object had been perfectly consistent. No signs of drift, no deviation, no irregular motion, even as plumes of gas vented from its surface. The interstellar traveler held steady on its predicted course. Observatories across the globe, from Hawaii to Chile, verified the same thing: zero non-gravitational acceleration. Nothing unusual at all. But then, at the height of its solar exposure, during one of the Sun's most turbulent activity cycles in decades, it shifted, only slightly, but enough. Enough for NASA's Jet Propulsion Laboratory to detect a trajectory change greater than 99% of all known comets. Enough to ignite a question no one was prepared to face. What kind of force could cause that kind of motion at 1.36 astronomical units, where solar heating should be far too weak to generate such thrust? The change wasn't random. Its timing, its direction, its accuracy, all appeared intentional. And what made it even more remarkable was that a Harvard astrophysicist, Avi Loeb, had already suggested that a maneuver might occur precisely at that point. Tonight, the evidence is undeniable. The celestial body, once labeled 3I Atlas, has veered off its expected path, not toward Earth, but in the direction of something far more mysterious. Let's begin. For months, astronomers had watched 3I Atlas drift across the darkness, steady, unchanging, a silent wanderer, governed by the same cosmic laws that have shaped every comet's journey since the birth of orbital mechanics. Its approach toward the inner system was clear, its speed unwavering, its rotation stable. Every new dataset confirmed what physics predicted: an object of this mass and momentum should behave exactly as gravity commands. And for a time, that's precisely what it did. Night after night, observatories across both hemispheres recorded its position with near-perfect accuracy. The Minor Planet Center updated its orbital elements, and every computation lined up flawlessly. No drift, no subtle nudge, not even a hint of non-gravitational interference. It was as if 3I Atlas existed in a perfectly frictionless reality, immune to the chaos that normally defines cometary motion. But perfection, as every astronomer knows, doesn't belong to comets. They're messy, volatile, alive with motion. They shed gas, they tumble and spin, unpredictably. Their surfaces burst with jets of vaporized material that subtly change their courses. These deviations, known as non-gravitational accelerations, are small but measurable. In nearly every case, they're unavoidable. A single burst of escaping gas can shift a comet's velocity by millimeters per second, which, over time, moves it thousands of kilometers off its expected path. Astronomers anticipate this. They factor it into their orbital models. Yet, 3I Atlas refused to obey. From early September through late October, it displayed every visible hallmark of an active comet: a glowing coma, a delicate tail, and spectral readings confirming the presence of CO2 and cyanogen emissions. But despite all of that, its path through space remained uncannily precise. Not a single detectable deviation. NASA's Solar System Dynamics Group, which specializes in refining orbital parameters for active celestial bodies, quietly noted the anomaly in their internal records. No detectable non-gravitational parameters required. It was a sterile phrase, almost bureaucratic, but it concealed something astonishing. It meant 3I Atlas was expelling gas without experiencing any recoil. To grasp how strange that is, consider what normally happens when a comet draws near the Sun. The heat causes its frozen compounds, carbon dioxide, methane, even water, to sublimate directly into vapor. As this gas escapes into space, it exerts a backward push on the comet's core. The same principle that propels rockets through space: exhaust expelled one way, motion generated the other. Every known comet, from the tiniest fragments to Halley's famous giant, follows this rule. The recoil is inevitable, but not here. In early October, the Pan-STARRS Observatory detected steady activity from 3I Atlas, consistent with an active nucleus several kilometers across. Its coma brightened, scattering sunlight in patterns that suggested a vigorous release of dust and gas. Under normal circumstances, that should have induced at least a few micrometers per second squared of measurable acceleration. Yet, multiple tracking passes showed no such effect. The object moved as though frozen in its own trajectory, an active comet with no measurable recoil. It was like watching a rocket ignite and remain still. The equations simply didn't balance. At first, scientists attributed the mismatch to observational error. Perhaps opposing jets of gas were firing symmetrically, cancelling each other out. Or maybe the entire surface was venting so evenly that every thrust vector neutralized the next possible. Yes, but only barely. The level of symmetry required bordered on artificial perfection. Natural cometary surfaces are jagged, pitted, fractured by countless years of radiation and micrometeoroid impacts. The odds that one could vent gas in perfectly opposite directions for weeks on end were nearly zero. Still, with no better explanation, the symmetry theory held until the next anomaly emerged. Infrared readings from the Subaru telescope revealed that the composition of 3I Atlas was unusually dominated by carbon dioxide rather than water ice. An oddity for comets at its current distance from the Sun. Typically, water vapor drives most cometary activity around 1.3 astronomical units, while CO2 takes over farther out, where temperatures are lower. But here, the behavior was inverted, vigorous CO2 emissions near the Sun. Yet, no accompanying record. If CO2 truly made up the majority of its volatile materials, the thrust from sublimation should have been stronger, not weaker. The gas pressure from carbon dioxide sublimation can reach 10⁴ newtons per square meter, enough to create measurable acceleration even in massive cometary nuclei. Yet, once again, the data refused to comply. At this stage, analysts at JPL reprocessed the orbital data using more advanced computational models. They considered every known factor, planetary perturbations, relativistic effects, even the subtle pressure of sunlight itself. But nothing refined the fit beyond simple Newtonian gravity. The pure gravitational model remained the only one that worked. That's what unsettled everyone. When an active comet behaves with absolute precision, it's not a sign of order. It's a sign that something else is maintaining that order. Soon, amateur astronomers online began referring to 3I Atlas as the frozen vector, a poetic way of describing how its motion seemed locked in place. Some saw it as a curiosity, others as a quieter. If it's venting without recoil, one astrophysicist tweeted, then either momentum conservation is incomplete or something is cancelling it out. Behind closed doors, that something became the subject of intense speculation. Could its internal composition somehow absorb the forces generated by outgassing? Could invisible jets vent from beneath a porous crust, perfectly balancing one another? Or could electromagnetic interactions with the solar wind be stabilizing it in ways we don't yet understand? Each idea was tested, each failed. In the end, the simplest and strangest truth remained. 3I Atlas was active, yet motionless. It's easy to underestimate what that means. Every object entering the inner solar system experiences constant gravitational acceleration from the Sun and planets, plus small chaotic deviations from outgassing. When none of those irregularities appear, something extraordinary must be at play. Either a force we don't understand, or an object that behaves by rules entirely its own. By mid-October, its brightness plateaued. Photometric data showed minor flickers, but no dramatic surges. Its magnitude steadied near 12.5, even as it neared perihelion. The coma grew denser, more compact, as if the gases weren't dispersing freely into space. That density hinted at yet another mystery. Volatile compounds might be escaping through narrow vents, not open jets, compressing the activity rather than projecting it out.
A small number of researchers began to suggest an alternative possibility, that 3I Atlas might possess an abnormally strong outer crust, one capable of trapping sublimated gases beneath its surface, until pressure built to critical levels. If that theory were correct, it could mean only one thing: the stillness before a storm. a quiet buildup, preceding a sudden outburst. This wasn't just speculation. Similar events had been observed in the past. Comet 17P Holmes, for instance, erupted in spectacular fashion, its brightness increasing by more than 1,000-fold overnight, when internal gases ruptured its crust and blasted material into space. Those eruptions were dramatic, chaotic, unmistakable, but 3I Atlas gave no warning signs. It remained eerily calm, a beacon of stability where there should have been turbulence. While astronomers debated, the sun itself began to stir. By late October, solar activity had surged dramatically. A sequence of M-class solar flares erupted, culminating in a massive X-class event on October 28th, just one day before 3I Atlas would reach perihelion. Streams of plasma arced hundreds of thousands of kilometers into space, unleashing charged particles that flooded the same region through which the comet was passing. If 3I Atlas had any conductive or magnetic characteristics, that solar storm would have interacted strongly with it. But there was no way to know for certain. Astronomers had only optical and infrared data, no magnetometer readings, no radar reflections, just light and silence. The calm before the change was unnerving. Ground-based observatories, such as Lowell and Las Campanas, continued to log its coordinates through the thin windows of dawn and dusk, tracking every motion with growing anticipation. Each measurement reinforced what their equations predicted. No shift, no acceleration, nothing unexpected. Even after it crossed 1.4 astronomical units from the sun, the trajectory held steady. Then came the final 24 hours. On October 28th, a subtle brightening began. Not an explosion, but a quiet surge that caught attention nonetheless. Some scientists attributed it to simple solar illumination. Others whispered that something beneath the crust was beginning to move. The European Southern Observatory's automated systems noticed it too, a nonlinear increase in brightness, meaning the reflected light was climbing faster than geometry alone could explain. The difference was small, just a 15% rise, but it broke the pattern of calm consistency that had persisted for weeks. When perihelion finally arrived, every telescope was watching. NASA's Near-Earth Object Coordination Center, JPL's orbital mechanics team, countless amateurs, all waiting for confirmation that the visitor would behave as expected. For the first few minutes, it did. The projected trajectory matched perfectly with predictions, differing by only a few arc-seconds. The universe seemed to be following the script, until it didn't. At exactly 0437 UTC, the first signs appeared. A subtle but undeniable divergence in the data, not large enough to raise alarm, but significant enough to stand out. Over the next 6 hours, that difference grew, verified independently by observatories around the globe. By midnight, the deviation could no longer be dismissed. Something had forced 3I Atlas off its strictly gravitational path, and with that, the silence ended. What followed would shake even the most skeptical scientists. A sudden measurable acceleration, precisely at perihelion, that could not be explained by known physics. Initially, the numbers looked wrong. Telemetry from multiple observatories on October 29, 2025, showed a faint irregularity in the right ascension data, small enough to seem like noise. But as the hours turned into days, the pattern solidified. 3I Atlas wasn't just drifting, it was accelerating. The confirmation came from a source renowned for precision, the Jet Propulsion Laboratory's Orbital Determination Team in Pasadena. Their early models from October 27th fit perfectly, residuals under 0.2 arc-seconds, near mathematical perfection. But once they included the post-perihelion data, those residuals exploded tenfold. The old model no longer fit reality. When they recalculated, the anomaly revealed itself, a non-gravitational acceleration, acting directly away from the sun, measured at roughly 3. To most people, that figure might sound insignificant, but for orbital physicists, it was astonishing. At 1.36 astronomical units, solar flux is too weak to generate that level of thrust through normal sublimation, especially when there's no evidence of a dust burst or material ejection. Even more puzzling was when it happened. The acceleration began exactly at perihelion, not gradually, not after warming, but instantly, as if triggered by an invisible switch. JPL engineers double-checked their calculations against independent observations from the European Space Agency's Gaia mission and the Canada-France-Hawaii telescope. Every dataset matched. The deviation vector pointed straight away from the sun, consistent with gas venting, yet the magnitude exceeded what sunlight-driven sublimation could possibly produce. That contradiction would soon dominate astronomical discussions worldwide. When confronted with unexplained acceleration, scientists follow a methodical process. They check for atmospheric distortion, instrument drift, parallax errors, calibration mismatches. One by one, teams ruled out each possibility. Radar echoes from Goldstone confirmed the optical tracking. The shift was real. And instead of fading with time, it intensified. By November 1st, the object's path had diverged by more than 600 kilometers from its predicted orbit, far beyond what chance or measurement error could explain. For comparison, the famous interstellar object, Oumuamua, exhibited a similar, but much smaller deviation, 1/10 the strength, and it took weeks to detect. In the case of 3I Atlas, it appeared within mere hours. Speculation exploded. Some proposed that an uneven release of trapped CO2 or CO had suddenly vented, producing a burst of thrust. But no corresponding change in the coma was observed. Telescopes in Chile and Spain, monitoring the object continuously, saw no dramatic expansion of dust or vapor. The glow brightened slightly, but the structure stayed compact. Nothing like the explosive plumes typical of a volatile eruption. Others advanced the dust veil hypothesis. Perhaps 3I Atlas had expelled a dense cloud of microscopic particles too fine to be seen in visible light, but capable of generating recall. However, polarimetric instruments, such as those at the Nordic Optical Telescope, recorded no increase in light scattering. The brightness curve remained smooth and undisturbed. So the question deepened. What kind of force acts with measurable power, yet leaves no visible trace? NASA's internal memo on October 31st captured the confusion in a tone of clinical understatement. Observed deviation of 3I Atlas is consistent with a directed impulse event at perihelion. Mechanism undetermined. Magnitude exceeds typical sublimation-based acceleration by a factor of approximately 20. Behind that restrained language lay a profound mystery, one that no model, no equation, and no precedent could yet explain.
That multiplier of 20 quickly turned into a scientific obsession. Even the most erratic comets like 67P or Hyakutake rarely exhibit accelerations surpassing 10 meters per second squared at comparable solar distances. Yet for 3I Atlas to produce an acceleration of around 3 × 10⁻⁷ per it would have required a continuous expulsion of gas equal to several thousand tons, a discharge that should have been unmistakable, but it wasn't. The object appeared unnervingly calm. Its surrounding coma didn't expand, in fact it seemed to shrink slightly in the days after its closest solar pass. If anything, it looked less active. So what then provided that mysterious push? One early hypothesis, originating from a jet propulsion laboratory navigation engineer in a technical forum, suggested a brief, highly directional outburst. Not random diffusion, but something collimated, like material funneled through a narrow jet. If that release was extremely short-lived yet powerful, it could deliver a measurable impulse without drastically altering the coma's overall luminosity. But that idea carried a major problem. It required an unlikely buildup of internal pressure, the sort that a fragile, porous, rubble-like nucleus shouldn't be able to contain. Unless, of course, 3I Atlas wasn't a typical cometary body at all. Spectroscopic data hinted at something strange, high concentrations of carbon and metallic compounds, including traces of nickel and iron embedded in the dust spectrum. That mixture is rare for volatile-rich comets, but quite common in metallic asteroids. If 3I Atlas was even partially metallic, it could have tolerated far higher internal pressures before fracturing, theoretically allowing it to vent material through a narrow aperture, like a nozzle, generating a focused burst of propulsion. That might explain how it happened, but not why it happened precisely at that moment. During perihelion, the sun was violently active. Solar observatories logged multiple flares, including an M9-class eruption that hurled a coronal mass ejection directly across the ecliptic. Those charged particles would have reached 3I Atlas just hours before the anomalous acceleration was detected. Some physicists speculated that if the object possessed conductive or magnetically responsive properties, it might have briefly coupled with the solar wind in a way that generated a thrust-like electromagnetic interaction. That may sound fantastical, but electromagnetic propulsion isn't pure science fiction. Plasma interactions in space can exert measurable drag or acceleration on charged surfaces, though nothing anywhere near this scale has ever been observed naturally. Still, the data's precision forced a few scientists to confront a deeply unsettling possibility. What if 3I Atlas wasn't entirely natural? This wasn't a leap of imagination, it was born out of frustration. Every physical model failed to fit. The acceleration was real, precisely timed and remarkably smooth. There was no debris cloud, no fragmentation, no photometric chaos, just a clean, consistent thrust that subtly altered its course. When a system behaves too perfectly, scientists start searching for patterns, and then they found one. The direction of acceleration matched almost perfectly with the object's velocity vector, not with the solar radial line, as sublimation-driven jets typically do. Outgassing forces usually act perpendicular to a comet's surface, creating off-axis drift. A force aligned with motion implies something different. Thermal pressure doesn't fit. Propulsion, on the other hand, could. Coincidence, maybe, but the precision of that alignment was deeply unnerving. By early November, whispers about the anomaly began spreading beyond the research community. Amateur astronomers noticed deviations between updated orbital data and prior predictions. The offset was minor, about 0.02 degrees, but unmistakable. Online astrometry forums exploded with speculation. Non-gravitational parameter detected. NG term confirmed. Atlas behaving like Oumuamua 2. Officially, NASA described it as a transient acceleration consistent with gas-driven activity, but their bulletins grew more cautious in tone, each word carefully chosen, consistent with meant possible, not proven. Behind the scenes, researchers couldn't ignore the eerie déjà vu. The year 2017 still haunted many, the year Oumuamua passed through, displaying its own inexplicable acceleration. Back then, Harvard astrophysicist Avi Loeb had proposed a controversial theory that the motion might be due not to gas release, but to radiation pressure on a thin reflective surface. A light sail, mocked by some, defended by others. The idea never fully died. Now with 3I Atlas, the data felt eerily familiar, but stronger, sharper and more deliberate. In fact, Loeb had once suggested that if an interstellar object were under control, perihelion would be the most efficient window for a maneuver, when solar radiation and gravitational assistance peak together. The new readings from 3I Atlas seemed to echo that logic almost too perfectly. At 1.36 astronomical units, solar heating is mild, sufficient to vaporize some ices, but hardly violent. Yet the observed thrust implied a force-to-mass ratio far exceeding what sublimation alone could achieve, suggesting perhaps intentional modulation. NASA's own analysis estimated a change in velocity of roughly 5 millimeters per second. Insignificant on human scales, but enough to alter the object's long-term trajectory by thousands of kilometers. And crucially, the new path didn't aim toward Earth or any planet. It shifted outward and slightly north of the ecliptic, away from every major body in its vicinity. Random jets don't choose safe directions. This one seemed to. In the following days, telescopic tracking confirmed the change. The acceleration faded, then stopped altogether. 3I Atlas continued on a perfectly ballistic path, as if the event had completed exactly what it was meant to. When scientists reconstructed the sequence, a chilling precision appeared. 0437 UTC. Perihelion reached. 0441 UTC. Acceleration begins. 0452 UTC. Maximum deviation recorded. 0605 UTC. Acceleration ceases. 90 minutes. That's all. In that brief window, an object traveling over 200,000 kilometers per hour had shifted its course without any visible trace of why. No known natural mechanism can explain both the strength and brevity of that impulse. Sustained sublimation would cause gradual drift. Explosive activity would leave debris and chaotic rotation. Only a focused, time-limited burst could produce something so surgically precise. And so we're left suspended between physics and speculation, data and disbelief. In science, anomalies usually fade as new information fills the gaps. But this one refused to disappear. It survived scrutiny, cross-checks, and even matched predictions made years earlier. That's not coincidence. That's evident. Publicly, NASA's language remains careful, a short-lived non-gravitational event consistent with outgassing. But behind those words lies unease. Everyone involved knows this wasn't normal. Something nudged 3I Atlas, something deliberate, precise, and restrained. And it happened while the world was watching. The next phase of investigation, verifying the data, checking for repetition, and comparing with historical anomalies, would inevitably lead back to the only other visitor that behaved this way, Oumuamua, and that's where this mystery deep.
When the first reports arrived at Jet Propulsion Laboratory, they slipped in quietly among stacks of ordinary updates. Another orbital refinement, another cluster of observational logs from telescopes scattered across 3 continents. But as soon as the latest readings were processed, the atmosphere inside JPL's navigation division began to shift. Subtly at first, then completely. The data wasn't just odd, it was alarmingly precise. This was exactly the kind of enigma JPL's orbit determination team was built to solve. Their expertise lies in tracking the paths of asteroids, comets, and spacecraft, with microscopic precision down to fractions of milliseconds. Every reflection of light, every motion vector, every mathematical residual, measured, modeled, balanced. But this time, 3I Atlas refused to obey the math. The earliest warning appeared in a small but telling dataset from the Mauna Kea Observatory. Normally, astrometric residuals scatter randomly, forming neat, symmetrical clusters. This time, they began drifting systematically outward from the sun. Analysts first assumed mundane causes: atmospheric interference, turbulence, optical distortion, even calibration errors. So they set the data aside as unreliable. Then came confirmation when cross-checks from Las Campanas Observatory in Chile and Mount Lemmon in Arizona were processed. The same pattern appeared again, identical in both direction and magnitude. That's when JPL's lead navigation engineer, Dr. Sarah Hoffman, officially opened an anomaly report. Her note read, "Deviation vector confirmed. Magnitude exceeds 3 sigma from model prediction. Possible non-gravitational influence." In plain English, something unseen was pushing the object. Over the next 48 hours, the lab moved into full analytical overdrive. The orbit of 3I Atlas was recalculated using both Find Orb and JPL's proprietary dynamical solvers systems that incorporate planetary perturbations, solar radiation pressure, relativistic corrections, and even the subtle Yarkovsky effect caused by uneven heating. But no matter how they adjusted the parameters, the data refused to cooperate. The orbital model only fit if they added an extra acceleration term, one that acted radially outward from the sun and decayed exponentially over time. They labeled this new variable the standard coefficient for sublimation-driven acceleration used in comet models. Under normal conditions, A1 values hover around 10 bar-sest meters. The model demanded roughly 3 to 10 bar-7 bar-sest, 20 to 30 times stronger than anything expected at that solar distance. Hoffman's handwritten note on the report read, bluntly, unphysical unless driven by directed jet or unknown mechanism. When that remark reached JPL's internal science channel, it ignited a debate that lasted for days. The first to challenge it was Mark Chen, an orbital physicist specializing in cometary dynamics. "You're assuming isotropic sublimation," he countered. "What if the gas outflow is highly collimated?" Hoffman responded with a single graph: brightness versus time. The curve was flat. If there were a jet powerful enough to create a 1/7 bar-sest, you'd see at least a half-magnitude increase in brightness. We doubt it was the end of that argument. The team pivoted to photometric data. Using input from the Las Cumbres Observatory Global Telescope Network, they reconstructed a detailed brightness curve
around perihelion. It showed no significant change. The comet had been brightening steadily for weeks, then reached a plateau. No spike, no flare, no visual evidence of an outburst. The paradox deepened: acceleration without visible reaction, thrust without combustion. By October 31st, the anomaly was formally escalated to NASA's Near-Earth Object Coordination Center in Washington, D.C. The internal memo used unusually cautious language. Preliminary orbit determination of 3I Atlas indicates anomalous non-gravitational acceleration near perihelion, whereby 1.36 AU. Mechanism under investigation. 2 hours. That was it. Whatever had acted on the object did so abruptly, precisely, and then stopped. JPL analysts attempted to quantify the total impulse. Integrating the acceleration over the 90-minute window yielded a dV delta V of about 0 bar. Insignificant for a spacecraft, but in celestial mechanics, that's colossal. Over interplanetary distances, a push that small translates into tens of thousands of kilometers of orbital deviation within months. One engineer described it vividly: it's like blowing gently on a bowling ball and watching it miss the pins by a city block. The deeper they probed, the stranger it grew. Radar pings from NASA's Deep Space Network returned nothing. The object was too faint, too absorbent. Yet optical spectra hinted at metallic inclusions, nickel, perhaps iron, matching earlier observations from the Subaru and Lowell observatories. If 3I Atlas contained metallic structures, it could, in theory, interact with electromagnetic field. That realization led plasma physicist Dr. Elena Marino to propose an experiment. What if this isn't gas thrust? She asked. What if it's magnetic coupling? Her idea was simple, yet radical. A conductive body moving through a dense region of solar wind could experience Lorentz forces, generating a small acceleration, especially if the body possessed a residual magnetic field. She ran simulations of the solar conditions at 1.36. The solar wind density peaked at 18 protons per cubic centimeter high, but not extreme. Her conclusion was blunt: electromagnetic coupling insufficient by factor at. Hypothesis rejected. The mystery only deepened. Every anomaly begs for precedent, so the team looked backward to Oumuamua's 2017 flyby. That interstellar visitor had also shown an inexplicable acceleration of about 5 guys 10 bar 7 near 1 AU, controversially attributed to radiation pressure on a thin reflective body. But 3I Atlas didn't fit that pattern. Its acceleration vector was not aligned with the sun's rays. It was offset by nearly 15 degrees. That discrepancy haunted Hoffman. Radiation pressure, she noted, is geometry law. Photons always push directly outward from the light source. If the thrust is angled, something's steering it. By now, whispers had begun to escape the lab. Amateur astronomers and data analysts in encrypted forums started speculating, some nicknaming the object Atlas III, as if acknowledging it was something altogether different. A few claimed it was responding to solar flares, as though the perihelion acceleration had been not triggered. Inside JPL, no one dared use that phrasing aloud, but everyone understood exactly what it implied.
On November 2nd, Hoffman compiled a comprehensive trajectory reconstruction file, merging every observation from discovery to post-perihelion, each one carefully weighted by precision. She fed the complete dataset into JPL's Horizon system and ran the full computation overnight. When she arrived the next morning, the residuals had finally stabilized. The model aligned perfectly, but only after introducing a single impulse parameter, one occurring exactly at 0441 UTC on October 29th. The program didn't call for any slow or lingering force. It demanded a brief, concentrated acceleration burst, 90 minutes long. When visualized on a plot, it resembled a spacecraft burn, not a cometary drift. The numbers didn't lie. That same afternoon, an internal message circulated through JPL's navigation network. The subject line read, 3I Atlas Trajectory Update 17 from S. Hoffman. Its contents were as follows: Revised fit converged with discrete delta V event at perihelion. Non-gravitational acceleration magnitude 3 diary and is set. Direction per 4 diary from velocity vector. Impulse duration 5,400 seconds. Post-event orbit ballistic, no fragmentation signatures observed. Recommendation: maintain independent verification prior to publication. That email, later leaked anonymously, became the first semi-official admission that 3I Atlas's sudden course change was real, and more troublingly, that it behaved like a deliberate maneuver rather than a random outgassing anomaly. To the engineers, it was merely data. To the astronomers, it was a fracture in the laws of cometary dynamics. But to Avi Loeb, it was vindication. Weeks before, Loeb had speculated that if the object possessed any artificial characteristics, perihelion would be the optimal moment for an intentional trajectory change, leveraging the gravitational assist effect, just as spacecraft do when performing solar flybys for efficiency. At the time, his remark was dismissed as playful conjecture. Now, it read like prophecy. When journalists reached out for comment, JPL declined. NASA's official statement, released November 3rd, was notably brief. Current trajectory models of interstellar object 3I Atlas indicate a small non-gravitational acceleration near perihelion, consistent with outgassing activity. Further observations are required. Behind closed doors, that word consistent had become institutional shorthand for we have no explanation. Inside the analysis division, silence settled over the monitors. Every few hours, new telemetry arrived, and each update confirmed the same truth. The revised orbit fit perfectly. The anomalous thrust had ceased. As suddenly as it began, whatever force had acted on 3I Atlas was gone. And yet, something about that 90-minute episode refused to fade. There was no debris, no coma fragmentation, no radio spike, no thermal signature, just motion, just 90 minutes that reshaped the object's entire path. Hoffman's final internal note read almost like an open confession. If natural 3I Atlas may represent a previously unknown form of sublimation dynamics, if artificial implications exceed current analytical scope, it was the closest JPL came to acknowledging the unspoken possibility. In Pasadena, the night shift continued quietly. The lab's monitors glowed with a soft green trace, one thin arc sweeping away from the inner planets, bending gently toward the dark. The numbers had stabilized, the equations balanced, yet no one felt closure. Because deep down, everyone staring at that glowing line shared the same realization: precision doesn't come from chaos. And for the first time in years, Jet Propulsion Laboratory found itself observing something that behaved less like a rock and more like a decision. At 1.36 astronomical units from the Sun, the laws of thermodynamics are supposed to be straightforward. Every comet observed at that distance behaves within predictable limits. Water ice sublimates, carbon dioxide vents outward, dust brightens the coma. The solar energy input is calculable, dependable, constant. But 3I Atlas had shattered that framework completely. Nothing in astrophysical literature accounted for a thrust spike that's strong at that distance, not without an eruption or a measurable flare in brightness. To grasp why this number mattered, imagine what 1.36 AU really represents. Roughly 203 million kilometers from the Sun, beyond Earth's orbit, yet close enough for sunlight to deliver around 5. That's sufficient to gently warm a comet's surface, causing mild sublimation, but not to produce explosive energy releases. It's the quiet zone of the inner solar system, where comets behave gently, predictably, and fade in peace. 3I Atlas was supposed to do the same. Yet when its acceleration profile was compared to the solar flux, the math collapsed. The recorded impulse required more than 10 times the available solar energy. The Sun simply couldn't have powered that much thrust. Researchers scrambled for explanation. Maybe the surface was darker, absorbing more heat. A low albedo could, in theory, trap sunlight and boost sublimation efficiency.
but that would also make the object brighter in infrared, and it wasn't. Observations from Spitzer and Vista telescopes confirmed no infrared excess. The object absorbed and emitted energy, like any ordinary rocky nucleus. In other words, nothing special. Another hypothesis emerged. Maybe buried volatile gases had built up beneath a sealed crust and exploded outward. That could account for the energy gap, but not the timing. Random outbursts don't align perfectly with perihelion. They happen erratically, triggered by cracks or stress fractures. Yet this event occurred exactly at the sun's closest approach, as if responding to a signal. Then came the most puzzling detail of all. The direction. The acceleration vector wasn't random. It pointed radially outward from the sun, offset by just 14 degrees. If this were chaotic venting, the direction would fluctuate wildly over time. But during the entire 90-minute episode, the thrust stayed low. Someone at JPL muttered under their breath, half joking, "That's not physics, that's piloting." No one laughed. What made 1.36 AU such a problem was its position on the razor's edge. Too warm for inert rock, too cold for violent activity. Inside 1 AU, sunlight is fierce enough to vaporize ices rapidly. Beyond 2 AU, ices freeze into dormancy, but 1.36 AU sits at the fragile balance point, where changes should be slow and steady. No natural mechanism could produce the abrupt impulse seen in the data. The thermal curve was too flat, the physics too calm. So the question turned from how to where did the energy come from. Some looked toward the sun itself. On the same day as perihelion, a coronal mass ejection swept across the ecliptic, ejecting billions of tons of plasma. Could electromagnetic forces have nudged the object? The math said no. Even at maximum strength, the CME's magnetic pressure was millions of times too weak to generate such motion. Others speculated about electrostatic discharge. Perhaps 3I Atlas had built up charge and released it violently. That, too, failed the numbers. Whatever had pushed it had done so with precision, control, and silence. Once again, the equations refused to balance. The numbers betrayed every assumption the models stood on. The surface area was far too limited, the mass far too dense, and the force that should have emerged from it practically negligible. By November 3rd, researchers had begun referring to it informally as the 1.36 AU problem. Every proposed explanation collapsed under the same constraint. There simply wasn't enough solar energy available. It wasn't just a data irregularity anymore. It had become a thermodynamic contradiction. And then, the telescopes revealed something even stranger. The coma, that faint halo of gas and dust surrounding every active comet, looked denser after perihelion, not thinner. According to the laws of cometary physics, if 3I Atlas had lost massive amounts of material during its acceleration burst, the coma should have expanded, diffused, and faded. Instead, it appeared to tighten, as though the expelled material were being pulled back, or compressed, around the nucleus. Observers described it as a thin, glowing shell, clinging to the core, an almost self-contained luminescence. Amateur astronomers noticed it too. Across online forums, users compared pre- and post-perihelion photographs. "It looks more solid," one comment read, "like the light isn't scattering anymore." That observation hinted at something profound: structural integrity, not the loose, porous fragility typical of comets. Something about its reflectivity and density suggested a surface composition closer to metal or stone. Then came the spectroscopic results. The European Southern Observatory released preliminary findings, showing an anomalously low dust-to-gas ratio. In normal comets, dust dominates, scattering sunlight and creating the coma's glow. But here, the gas took over, and it was unusually faint, suggesting it was made of heavier, less reflective molecules, possibly metallic vapor. Among the traces detected was nickel tetracarbonyl, a compound almost never seen in space, and one that can only form under high-temperature, industrial-like condition. On Earth, nickel tetracarbonyl is a highly volatile compound, produced when carbon monoxide reacts with metallic nickel under controlled heat conditions, found in manufacturing environments, not frozen cometary surfaces. Its detection near 3I Atlas was beyond strange. It was nearly impossible for a natural object. Of course, the skeptics pushed back. Spectroscopic readings, especially at faint magnitudes, can deceive easily. Calibration errors, noise interference, misinterpretation, all plausible. But even the most cautious analysts couldn't ignore how uncanny the timing was. An object accelerating in an energy-deficient zone while simultaneously producing industrial-grade compounds during perihelion defied coincidence. One by one, the conventional hypotheses fell apart. Sublimation, too weak. Solar wind, too faint. Electrostatic discharge, too unstable. Magnetic drag, too inconsistent. The final natural fallback was mechanical venting. The idea that internal gases might have escaped through a narrow fissure, like a jet of air escaping a pressure valve. If that vent was small and directional enough, it could produce a short, controlled thrust. Theoretically plausible, if 3I Atlas were engineered, but that assumption required an absurd degree of geological precision, in a body supposedly made of fractured ice and dust. And even then, it didn't explain the exact timing, why the burst happened precisely when sunlight peaked, or why the direction remained perfectly steady. At 1.36 astronomical units, randomness should rule. Instead, the data spoke of deliberate order. By this point, Avi Loeb's name had resurfaced in every internal memo and discussion thread. His earlier prediction that perihelion would serve as the ideal maneuver window, if 3I Atlas were artificial, sounded eerily prescient. Quietly, a new phrase began circulating among the analysts: thrust optimization. It was a term used for spacecraft operations, maximizing efficiency by performing propulsion burns near gravity well. If this object had exploited the sun's pull to amplify its acceleration, the math fit perfectly, but such speculation was strictly off-limits in official documents. It existed only in whispered conversations, scrawled in private notebooks, exchanged between colleagues who didn't want to be quoted. Even those who rejected the artificial theory agreed on one point: the acceleration was too perfect. The impulse didn't flicker, didn't ramp up or taper off. It appeared, held steady, and then vanished cleanly. A textbook thrust profile, and in the entire recorded history of cometary observation, nothing like it had ever been seen. As data stabilized, trajectories recalculated, and the post-perihelion orbit finalized, a quiet but inescapable conclusion began to form. 3I Atlas had received a measurable impulse, at a time and place where no natural process could have produced it. The sun wasn't powerful enough, the chemistry wasn't volatile enough, the structure wasn't unstable enough. At 1.36 astronomical units, a distance where the universe should be calm and predictable, something had accelerated instead. And that left one unanswered question, echoing in every lab, every observatory, and every unrecorded meeting across the scientific community. If not the sun, then when the acceleration data was finally released to the public, the immediate instinct of the scientific world was to contextualize to test whether 3I Atlas was truly unique. Researchers compared it to every comet ever logged, hoping to find a twin, or even a faint echo of similarity. They scoured archives at the Minor Planet Center, the Sloan Digital Sky Survey, and NASA's non-gravitational force catalogs, spanning decades. The search was exhaustive. The results, absolute. There was nothing like it. Most active comets around 1.3 AU show non-gravitational accelerations in the range of 10, and those were catastrophic, visible even to amateur telescopes, leaving million-kilometer dust trails behind. 3I Atlas, however, remained compact, silent, controlled, yet its acceleration exceeded Holmes at its most explosive. When plotted, it stood completely alone, a data point without neighbors. The University of Maryland's Comet Dynamics Group produced the first comparative chart mapping solar distance versus acceleration magnitude for over 2,000 recorded comets. The results formed a smooth downward slope. The farther from the sun, the weaker the acceleration. At 1.36 AU, the theoretical upper limit should have been 5 times. That outlier spread across astronomy circles, like a rumor turned into data, and when composition comparisons were made,
the mystery deepened further. Typical comets near 1.3 AU display strong water vapor lines at 2.7 microns, clear signatures of H2O-driven activity. 3I Atlas did not. Its spectral analysis revealed dominant emissions of carbon dioxide and carbon monoxide gases typically found in comets far beyond the Sun past 3A. Yet here it was, within the inner solar system, behaving like something from the distant cold. Its chemistry spoke of the outer reaches, its trajectory betrayed inner solar dynamics, and its structure whispered something else entirely. At the European Space Operations Center, data teams launched thousands of Monte Carlo simulations, each one constructing a virtual comet with randomized vent locations, thrust strengths, and rotational speeds. Every model was allowed to evolve naturally under solar heat to see if chance alone could mimic the observed course shift. None could. Not one of those digital comets achieved the kind of perfect 90-minute directional impulse that 3I Atlas had executed. Even under the most extreme variables, randomness only produced jitter, unstable bursts, chaotic motion, never precision. Statistically, the odds of such exact timing arising by chance were less than 1 in 100,000. Next came luminosity analysis. Normally, when comets accelerate, they flare, simple physics. Expelling mass means increasing brightness. In nearly every known case, the most intense accelerators are also the brightest. But 3I Atlas refused to follow that script. It neither abrupted into a flare, nor dimmed post-event. Its total brightness traced a calm, nearly flat curve, with only a faint ripple near perihelion, a whisper of disturbance, then stillness. That ripple's energy signature was far too faint to account for the recorded thrust, as if whatever force was applied had done its work, invisibly. Each attempt to classify the anomaly only deepened its strange. Thermal models assuming water ice as the main surface component required an absurd sublimation rate, roughly 10·7 kilograms per second, the output of a geyser the size of a major city. To produce such thrust without shattering the nucleus implied internal strength and density iron-nickel, perhaps even alloyed material. None of those belong to a natural comet. They belong to engineered matter. By mid-November, the scientific focus had shifted. The question was no longer what it was like, but why it stood alone. Statistically, 3I Atlas didn't just deviate. It isolated itself entirely from all known datasets. Its non-gravitational parameters existed outside every recognized boundary. Most striking was its near-perfect A1-A2 ratio, the balance between radial and tangential acceleration. In comets, this value is usually erratic, shaped by chaotic outgassing. But here, it looked deliberate, balanced as though designed. Naturally, comparisons to Oumuamua, the first confirmed interstellar visitor, emerged. That object too had demonstrated unexplained acceleration after its solar pass. Yet even this parallel offered little comfort. Oumuamua's thrust was weak, steady, and aligned with solar radiation pressure. 3I Atlas, by contrast, delivered a short, powerful, precisely timed burst, the difference between a leaf caught in wind and a dart launched by intent. Some suggested 3I Atlas might be a shard, a fragment from a larger interstellar body, still chemically active within. But spectroscopy ruled that out. If it were a fragment, its composition would vary across its surface. It did. Its readings were remarkably uniform, almost as if it had been carved, not broken. In conference rooms and online symposiums, scientific language began to shift. Terms like thermal outgassing and surface venting faded, replaced by careful phrases: timing anomaly, coordinated impulse, energy discrepancy. When patterns no longer fit, vocabulary bends for. The data kept whispering a single story. The acceleration vector was angled 14 toes from the solar radial. Duration, 90 minutes. Intensity, 20 times beyond any thermal explanation. Afterward, its motion stabilized instantly, as though a controlled maneuver had been executed, and concluded. The first time the word maneuver appeared was in a marginal note from a jet propulsion laboratory analyst on November 6. Not an official term, but a quiet acknowledgement that something extraordinary had occurred. To regain perspective, researchers expanded their datasets, comparing every known cometary course shift, Encke's gradual drifts, Halley's long-term deviations, Shoemaker, Levy 9's chaotic breakup.
Each displayed noise, fragmentation, brightness spikes, signatures of disorder. 3i Atlas showed none. Its event was sharp, clean, singular. Even when normalized for mass and surface area, the thrust-to-mass ratio aligned disturbingly close to spacecraft propulsion, roughly 1.2. That was not proof of design, but it was a number that unsettled everyone. Broader comparisons made the unease worse. No interstellar body, not Borisov, not any candidate tracked by pan-stars, had ever exhibited such behavior. Theoretical models of drifting interstellar debris suggested tumbling chaos, not calculated control. 3i Atlas didn't behave like a wandering rock. It behaved like something with vector intent. Eventually, the lack of natural precedent became the loudest clue. When no randomness remains, order feels deliberate. By mid-November, synchronized data between NASA's JPL and the European Space Agency confirmed a revised orbital path. 3i Atlas was no longer tracing a typical exit trajectory. It had pivoted upward, away from the ecliptic, angling out of the solar plane, as though seeking the dark. The shift wasn't chaotic. It was graceful, efficient. Whatever had happened, it had pushed the object toward colder space, dimming quietly as it departed. When the final comparative analyses were published, the closing line of the abstract was understated, yet chilling. 3i Atlas exhibits an anomalous non-gravitational acceleration, unmatched among all known cometary or interstellar bodies. Scientists rarely use That sentence alone felt like a collective surrender, a reluctant admission that something beyond current physics had just brushed through our system. And though few said it out loud, the unspoken conclusion echoed through every observatory. Whatever 3i Atlas was, it hadn't merely reacted to the sun. It had chosen its path.